magazine, and I wrote a book called Software Toolbox for Real-Time Programmers. And the reason we're here today is because I worked on Project Apollo and things even before Project Apollo for NASA. Would you like to know more? I'm going to take that as a yes. I was graduating from college in 1959. I interviewed a number of organizations, and one of them was NACA, which stands for National Advisory Committee on Aviation. That was founded back in 1913 or something like that. So I was, hoping I would get an offer from them in Langley, Virginia. Well, the offer letter came, and it was, I wish I still had that letter. It was on NACA stationery, and some secretary had crossed out the C and put an S above it. So basically, in the time that it took between the interview and the offer, NACA had been changed to NASA. I went to work there in April '59, and went to Langley, Virginia. I went to the Theoretical Mechanics Division and worked with a wonderful bunch of people, very small group, called the Lunar Trajectories Group. That name, I guess, tells you everything. Very small group. My boss was a fellow named Bill Michael. If you Google Bill Michael, you'll find a lot of information on him. He was involved in the debate over LOR versus Earth Orbit Rendezvous. You may remember, older folks may remember that. Robert Tolson was a colleague. He's also a helper on the part-time scientist group. So I think we have a sort of a unique situation in the sense that we have two of the original members of the Lunar Trajectories group, which only consisted of 5 people. So that's pretty interesting. You've all seen the figure 8 trajectory. That's the circumlunar trajectory. It shows up everywhere, anywhere, anytime someone talks about lunar missions. Bill Michael and I were 2 of the first 4 people to write a paper on that. We wrote that in 1961. I did a lot of studies on that using a restricted 3-body program. Maybe I should pause here and just point out Newtonian physics and Newtonian trajectories has got to be one of the purest applied math efforts in history, because you've just got a few masses which can be treated as point masses flying around each other and affected only by gravity. So it's a very clean environment. Unfortunately, the problem itself is not all that clean. If you look at the relationship, say for Mars orbit, it's basically a 2-body problem, Sun and Mars. Nothing else matters. Same with Sun and the Earth, out of the Earth-Moon barycenter. But the motion of the Moon is a very complex thing, because the Sun perturbs it not negligible amount. So an accurate computation of the Earth, Sun, Moon system, and for the throw a spacecraft in there, is a 4-body problem, and there's no easy solution for that. Way back in Newton's day, people like Lagrange worked on, they tried to get a simplified solution, and they worked out the restricted three-body model, which has only the Earth and the Moon moving in a plane and the trajectory of a spacecraft in the same plane. Actually, they were interested more in the motion of a comet in the solar system, but the math is the same. We had a restricted three-body program, and that's what I used for my studies. In 1960, I left NASA and went to work for General Electric. Basically, I followed the money. General Electric had been given a contract to do pre-Apollo studies, basically study the whole problem of getting to the moon and back. And I was hired in to help with that. And later on, there was a huge proposal effort for the production contract, which GE spent a lot of money on and worked very hard on. Unfortunately, they lost to North American. And there's some stories about skullduggery and the government that send that contract to them, but I won't go there. We were very disappointed in it. We did get a contract to do what they called reliability assessment, which was basically what's the probability that the astronauts will come back alive? That was number one. And what's the probability that we'll complete the mission? So we had a huge efforts to answer those two questions, and a big computer program calculating the things that could go wrong. I was not too involved in that part. I continued with trajectory work. Let me back up and say that at GE I was responsible for all of the trajectories generated for the Apollo program, the study contract, and all that. We used an in-body program for that effort, and there was a lot of interesting stuff came out of that. You have to remember, this was 1960. Computers were brand new. I think the IBM 702 was out some years before. I think it was around 1955, but nobody really had them until the Apollo effort started. There were maybe 3 or 4 IBM 702s being used for scientific work before the Apollo effort and for NASA, and quite a few after, because all of the contractors to NASA pretty much had to buy those computers. Not cheap. Now there's been a lot of talk about the power of these computers. Needless to say, an IBM 702 would not be a very impressive computer. Today it had 32K of RAM, no disks, only mag tape. So it was not a fast machine, but internally they did okay. And they had 36-bit word length, double precision floating point, hard floating point. You could get some things done. When I was at GE, we had 7094s, which were a good bit faster. And later on, I went and worked for a company called Mussler Corporation. And we worked with NASA George C. Marshall Space Flight Center in Huntsville. And there we had UNIVAC 1108s, CDC 6600s. And those guys were pretty fast in anybody's measure. The 6600 had a 60-bit word length and could really zoom. It was designed, I understand, by the same designer that designed supercomputers later. So we got a fair amount of work done.